This is Chapter 7, Earth and the Terrestrial Worlds. We're going to be looking at the four planets that we call terrestrial planets. The first one, of course, is Mercury. And as you can see from the inset there, Mercury's surface has craters. There are smooth areas, smooth plains, and there are also cliffs. Here's a photograph of Venus and another insert, another close-up. We see that Venus has evidence of volcanoes and some craters. This is a radar view of a twin-peaked volcano. So apparently there were two volcanic vents that reached the surface here. And of course Mars, outside our orbit, but still a terrestrial planet, has some craters. It appears to have some riverbeds, as you can see on the close-up on the left, and what we think is the largest volcano in our solar system over on the right. Our moon, although it's not a terrestrial planet, seems to have a similar origin as the rest of the terrestrials. We see craters, and we also see smooth plains like we did on Mercury. Earth is a bit different. Obviously, 3/4 of it's covered with water, but volcanoes are certainly present. Craters, although in lesser number, mountains of several different types, and of course, riverbeds. So, Earth is a planet. Why is Earth geologically active? What processes shape Earth's surface, and how does Earth's atmosphere affect the planet? Well, Earth is pretty geologically active. As you can see, the circles there on the left compared to Venus, Mars, Mercury, and Moon. The Earth is basically consisting of a rocky crust, a mantle, which has a higher density than the crust, and the metal core, which has a higher density of all of that. The crust can sometimes be called the lithosphere, as you see in the diagram. So that's the basic composition of the interior of our planet. Venus has a similar structure, although the core and mantle seem about the same size, the lithosphere about the same. Obviously, surface features are very different since it's inside our orbit. Mars, Mercury, and Moon have lithospheres, in other words, a solid surface. That's why they're called terrestrial planets. But their mantles and cores differ in size substantially. So going back to Earth's interior, we have a thick, very dense nickel and iron core. That's the highest density material. The mantle, which is considered medium density, but still has some fairly dense minerals. Lots of, as they're called, silicates, minerals that contain silicon and oxygen. And then finally the crust, which has the lowest density material. Granite and basalt are two good examples of what the crustal rock is made out of, at least the original crust rock. The interiors of the planets are derived from indirect evidence in most cases, and of course with Earth we have some seismographs that can detect just how the earthquake waves can pass through, so we have a pretty good idea of what the interior looks like. A long time ago, as the Earth first formed, we think the natural separation of different densities of rock occurred. That's called differentiation. The gravity pulls the higher density material to the center. The lower density material tends to rise, and the material ends up separated by their differences in density. And that seems to be true of all the terrestrial planets. The lithosphere is this cool, rigid rock, which is at the surface. It tends to, what some people call, float on the warmer, softer, more dense rock that lies beneath it. That's, of course, the mantle rock. Rock stretches when you pull it slowly, but breaks when you pull it rapidly, just like this taffy or special clay does. That can either cause rocks to bend but not break if the movement is slow, or they will break if the movement is fast. And of course, we see evidence of that whenever an earthquake occurs. So the gravity of a large planet like ours will pull slowly on the rocky content, shaping it into a sphere. The slow the slow pulling together actually causes the spherical shape. And of course, gravity is the biggest influence there. Heat is going to drive geologic activity on Earth, inside Earth, I should say. There is convection, which causes hot rock to rise and cool rock to fall within the mantle. And one of these convection cycles, as they're called, takes about 100 million years. So within the Earth, there's this recycling of mantle rock. And of course, that causes other things to be disturbed as well. What are the sources of that internal heat? Well, there's gravitational potential energy initially about 4.5 billion years ago as our Earth was forming. The differentiation caused, of course, the hotter rock to be hotter, more dense rock to be trapped near the center, and then radioactivity is still being given off by some of these minerals, some which have some very long, some which have some very short half-lives. But as we know, radioactivity generates a lot of heat. So our Earth, as it's cooling down or as it's aging, is still generating heat. This accretion and differentiation when the planets were young, of course, generated a lot of heat. But as we now know, radioactive decay is a very important heat source for the interior. So anything that's being heated, such as this mantle rock, is being heated due to radioactivity mostly. There are three ways the heat's transferred within the Earth. Convection transports heat as hot material rises and cool material falls. That's a natural process. It happens in the Earth's atmosphere too. And then conduction transfers heat from hot material to cool material by contact. In other words, as they're touching each other, they'll conduct heat. And finally, radiation sends some of that energy into space. So some of the thermal energy that the heat has had trapped inside and is reaching the crust and eventually the surface is radiating back into space. What about size? Well, smaller worlds cool off faster and harden earlier. So it's obvious that Mars, Mercury, and of course our moon, being smaller objects, did exactly that. They cooled off faster. So we think the moon and Mercury are pretty geologically dead as far as any tectonic activity or movement of plates or anything like that. Planets, if they have some sort of a metallic core, and that core is able to move, even though slowly it'll move, that can actually generate a magnetic field around the Earth, or around any planet, which, as we'll see in a little while, makes a big difference in the evolution of the planet. Here's a diagram and then, of course, a photograph of the Earth's magnetosphere or magnetic field. It protects us from charged particles from the sun, so that's a good thing. And of course, it can display what we call northern lights. Here, the aurora borealis. In the southern hemisphere, it's called the aurora australis. And that's just a reaction of our magnetic sphere or magnetosphere reacting to solar wind. It tends to generate a disruption of the electrons, and that emits photons or light. So the magnetosphere protects us from harmful solar particles, but it also lights up our sky when the photons are released. So how do we know what the interior of a planet is like? Well, for Earth, we look at the earthquake waves that pass through the Earth or around the Earth. There's basically two kinds of waves. The top slinky is showing you kind of a push-pull motion that the earthquake wave would generate, those are called P waves or primary waves. So P waves push matter back and forth. S waves, on the other hand, are shaking or secondary waves, shake matter side to side. Both types of waves are generated by an earthquake, but obviously the P wave travels faster because it's pushing and pulling in the direction of motion or in the direction the energy is moving. S waves travel considerably slower. So what happens is P waves can go through the Earth's core, but S waves don't. So we think that the Earth's core must have a liquid outer layer. If the S waves don't pass through it, that means they're lost in the transition or the movement from mantle to core. P waves can travel through. So there's a difference in the way that the waves travel. There's also a difference in how fast they travel. And that difference is important in actually determining where an earthquake occurs. So what processes shape Earth's surface? We see some differences in size, of course, of these objects, but we also see some differences in the nature of the surface of each. There's impact cratering, which has occurred and still occurs due to asteroids or comets or smaller objects such as meteors. There's volcanism, which is obviously the eruption of molten rock onto the surface. There's tectonics, which is the disruption of a planet's surface by internal stresses, and we'll talk about the different types here in a minute. And then there's erosion. The surface changes by wind, water, ice, things that tear the surface down, wear it down. So here's a nice little diagram showing what impact cratering can do. Of course, 4.5 billion years ago, there was apparently a lot of impact cratering. Craters themselves are sometimes 10 times wider than the objects that make them. So a large crater would be something indicating usually a much, much smaller object. But there are lots of small craters outnumbering the large ones, which to most scientists means there were many smaller particles bombarding the early solar system than there were extremely large ones. Here's two examples of an impact crater. Meteor crater over here on the left side is definitely that, an impact crater. Bits and pieces of the meteor or small asteroid maybe that hit are scattered throughout this area. The raised rim and the somewhat shaded areas around indicate that it truly is an impact crater. And then over on the right is a picture of Tycho, or the Tycho crater, which can be found on the surface of the moon, another impact crater. Volcanism, another process, happens when molten rock, or what we call magma, finds a path through the lithosphere and comes up and punches through the surface. Once it reaches the surface, we call that magma lava. So there's a difference in the name, although it's the same substance. And of course, associated with volcanic activity is the release of a lot of different types of gases. There are many, many gases trapped in the molten material that's reaching the surface. And so, although the picture shows a lot of cloud-like material, there's a lot of gases trapped within those clouds. Tectonics involves the movement of some part of the Earth's crust, possibly due to convection or conduction of material deep within the mantle. So convection of the mantle creates stresses in the crust, and that's called tectonic forces. Compression will sometimes force mountain ranges together, and of course a valley, or rift valley as it's called, can form where the crust is pulled apart. And we have examples of that both on the left and the right. On the left is a collision between the Himalayas and India, and on the right is a separation near the Arabian Peninsula and the continent of Africa. So the plates are actually pulling apart there, and on the left the plates are smashing together. Erosion is another process. It's a blanket term for weather-driven processes that break down or transport rock. And several of those processes are listed: glaciers, rivers, and wind. The Colorado River continues to carve out the Grand Canyon. It's a good example of river erosion. Initially, some people thought this canyon was due to fault action, earthquake activity, but it's been pretty well verified that what's happening here is all due to the Colorado River. Erosion by ice, such as you see here in Yosemite Valley, is due to a glacier carving out this, what some people call a U-shaped valley in cross-section. There's several different types of glaciers. This would have been a valley or mountain glacier that carved out this U-shaped bowl. And then there's wind erosion. Wind, depending on its speed, can carry different size particles, but it wears away the rock and builds up formations of that sand. We, of course, call them sand dunes. This is an example of what erosion can do. It can create new features by depositing the sediment. In this case, this is a river delta at the end of a river. So let's look at the atmosphere of the Earth very quickly. We have different wavelengths of light being radiated from the sun. Some wavelengths actually reach the Earth, like you see the yellow squiggly. That's, of course, visible light. Other forms of light do not reach the Earth's surface. But let's look at visible light here, for example. It may reach the surface, but then may radiate back out into our atmosphere. So if it does, that energy is turned into usually infrared energy, and that kind of energy can be trapped by clouds, haze, even the surface of the Earth. Some of it is absorbed within the atmosphere, and of course if there are gases such as carbon dioxide in the atmosphere, that's called a greenhouse gas. It can actually absorb and re-emit more heat. So depending on the clarity and the consistency of the atmosphere, that'll determine just how much heat is actually absorbed. So what are the effects of atmosphere on the Earth? Well, certainly erosion, wind, water, ice. It does offer radiation protection, which is good. We have something called the greenhouse effect, though, where visible light may reach the surface but then be re-radiated as some form of thermal energy, infrared energy. But it also makes the sky blue, which is kind of interesting. We are protected from harmful radiation such as X-rays because our atmosphere won't let them through it. It's absorbed. The same is true of most of the ultraviolet light that the sun radiates. But again, over on the right, we see all the colors, and those colors are, of course, visible light. Those do reach the surface, and they warm it. But as we saw earlier, the greenhouse effect is one where some of the energy that reaches the surface is re-radiated and possibly in the infrared, and that energy is absorbed by gases in the atmosphere. So we've seen this picture before, and this just kind of reinforces the idea that the Earth's atmosphere absorbs light at most wavelengths. So whether it's gamma rays or X-rays or infrared or radio waves or just infrared, there's a certain absorption to those wavelengths. It's visible and radio waves that actually can reach the surface. So what's a greenhouse gas? Well, it's any gas that absorbs infrared energy. And a good rule to remember is that greenhouse gases are molecules of two different types of elements. So for example, carbon dioxide, water, methane. Those are the three examples the book gives. Those are greenhouse gases because being composed of two different elements, they will absorb energy. Things that are not greenhouse gases are one or two atoms of the same element, such as oxygen or nitrogen, which of course is a major, those two are major components of the air we breathe. It's these other chemicals, these other molecules that will actually absorb energy. So, because of the greenhouse effect, Earth is much warmer than it would be without an atmosphere, but so is Venus. And of course, we know Venus has a much, much higher surface or air temperature. So let's quickly take a look at this phenomenon we see as with different colors of the sky. Atmosphere scatters blue light from the sun, making it appear to come from different directions. So as you can see, the person at the top of this globe, noon in Hawaii, is what they're showing. The blue light is being bounced around, and of course, that's what we see. What our eyes pick up is the blue. All the other wavelengths of light are absorbed. Near sunset, where we see this person in the diagram here, sunset in Florida, here's where the red light is going to be scattered as opposed to the other wavelengths. The red light is apparently then going to give us these beautiful sunsets. So what have we learned? Well, first to answer some questions about Earth. Earth retains plenty of internal heat because it's large for a terrestrial planet, and of course radioactive decay is a reason for that. The heat drives geologic activity, it keeps the core molten, and it drives geological activity. Convection is going to cause movement of the Earth's plates. And finally, the circulation of molten metal in the core generates the Earth's magnetic field. So thank goodness we have a magnetic field to protect us from some forms of solar radiation. What geological processes shape Earth's surface? Well, these are the four biggies: impact cratering, volcanism, tectonics, and erosion. And finally, how does Earth's atmosphere affect the planet? Well, it erodes the planet by several means. It does protect us from radiation, but it also introduces the greenhouse effect, which keeps the atmosphere and us warm. All right, section 2, Mercury and the Moon, geologically dead. What are the goals? Well, was there ever any geological activity on the Moon or Mercury? We see a lot of similarities between the Moon and Mercury here. We see cratering. We see what appears to be flat areas. So maybe they had a similar formation and evolution. Here's the Moon. Some volcanic activity we think occurred about 3 billion years ago, which may have flooded these originally what they were lunar craters. Now we call them lunar maria. And now, of course, we think the Moon is pretty much geologically dead. There appears to be no plate movement, no internal heating. It's just pretty much static as far as any geologic activity is concerned. So we think, going from left to right across this page, there was heavy impact cratering, big and large, and big and small impact craters. Some of those craters were filled with lava, creating these flat lands or maria, and that's what we see today. Cratering of Mercury was a mixture of heavily cratered and smooth regions like the Moon. And the smooth regions are likely ancient lava flows. You can see the picture on the left of Mercury, and what appears to be two rings, one inside the other, which could have been an impact crater, and it looks like something partially filled the crater. We still see the rim, but the majority of the crater bottom has been filled with what appears to be lava. This is over on the left is the Caloris Basin, largest impact crater on Mercury. And the region opposite the Caloris Basin is jumbled from seismic energy of impact. So not only was there impact cratering, volcanic activity, but over on the right, we think there was something happening there that caused Mercury to shift, cracks to form in its surface. So, tectonics on Mercury. Well, we have these long cliffs that Mercury must have shrunk early in its history. So this would be a place where The rocks weren't able to withstand the stress of shrinkage and cracked. We see these in a few places on the surface of Mercury. The lighter areas, which are obviously color enhanced, are thought to be hollows, formed as easily vaporized minerals escaped. So in other words, there were low temperature minerals here. Remember, Mercury is the closest planet to the sun, and those were able to vaporize.